introduce you to my senior colleague, or you can also say my teacher at some point, and even now.
Friend, you can say. Yeah.
Yes, thank you, Professor Madhav. So Professor Krishna, Madhav Krishna is a senior faculty at IIIT Hyderabad. He basically leads the robotics research group at IIIT. He has been with us for almost 17 years now, and he has been leading really through the front for IIIT for robotics domain. He is not just locally, but he has also been acknowledged to be, I think, top the 5th rank in the Asia for as a researcher and in robotics domain, and around 30 or 30. There are two or three ranking agencies, 40 in the world. And he has phenomenal, I think, rate at which he publishes to top conferences, almost 65 publications. At least I know every year there are 4 or 5 publications, and those who have worked with him or know the lab, knows the rigor he maintained in the lab. And at the same time, he is always like a student. Whenever new concept comes, whenever things that are out there and students are stuck, he helped them at the code level sometime also, but definitely at the concept level. So people really are, as is because I attended my first class in robotics. He was teaching in mobile robotics at IIIT.
So I think he is talking of someone else. I would certainly love to be what he is saying. But so
thank you. I would like to welcome him formally. And there are a lot of anecdotes I can go through, but there's not time for that because his time is more valuable. So thank you for coming, and he'll take us through the area of SLAM and robotics and whatever 3D concepts that are being used there. So welcome.
Yeah, thank you, Avinash. I think it is, certain things were over the board. So I think one thing which you said is I am senior faculty in the sense I work through my students, right? So many of these things which I would present are my students' work. And so if you have some really low-level details of it, I would answer it also through my students over emails and things like that, right? So the way this slide also, like I prepared a bit, but I was also helped by my student Omama for this preparation. So to be honest, that's just to say like how we operate. So we have taken this slide because there are a lot of equations and math. So we have copied from those some of these slides and put here. So we have used quite liberally from Cyril Stackner's photogrammetry slides, Fei-Fei-Li's epipolar geometry slide, and we have a very good lecture notes on mobile robotics, which has actually attracted a lot of attention, prepared by my student Shubodh in 2020 as a Notions page. As a matter of fact, the bundle adjustment and out there, especially, I think he does go at a pretty low level. So whatever I present here, the initial part, which is on the what I call as the SLAM pipeline, I would be doing both the monocular SLAM and the point cloud based SLAM. So what is it? The general flow of this. But then this involves a lot of intricate concepts, including homogeneous representation, homogeneous coordinates, projective geometry itself. So all of this, unless you are aware of it, if you're aware, then this first part may be like a kind of something which you know, maybe like a repetition. If you're unaware, then it may be slightly tricky to understand all in one go. But if you have any questions, so we can put you through the slide deck or through the Notions page. We also have a summer school in robotics, essentially for students who are joining robotics, where we go through 3D vision and SLAM in some detail. If you are inclined, then you can let us know. This school is typically free for all, but we don't advertise because of logistics. So but if you are keen for whatever reason, then you can let me know. So the talk itself is the first part. I would be doing the SLAM pipeline, and then the second part I will do some of these recent things which we have which we believe we have innovated over SLAM. One is this idea of topological SLAM. And the next one is the idea of what we call as augmented rotation invariant descriptors. By augmenting data to descriptors, we make them robust to rotation or large viewpoint changes. And how can that be brought into SLAM pipeline, especially for loop detections from opposite views and things like that. And this is a visual inertial SLAM in dynamic scenes. So these are a few things which I would touch upon. And also, this is an area which we have been, we had been working, say, from 2009 until 2020, 2021, which is the multi-body SLAM in dynamic environments. So I will touch upon these. And so I would answer whatever I can, whatever I am able to, and things which I'm not able to answer, you could contact me by email. Either I'll do it or I'll do it from my students. Okay, right. So the basic monocular SLAM pipeline, which is like, you have a single camera which is moving around. I'll play a video. So basically it takes images, right? I1, I2, IN, say. And then between two pair of images, it does the popular epipolar geometry, which goes out the fundamental and essential matrices. And then you decompose the essential matrix into 4 possible RNT and make use of chirality to choose the best rotation and translation, which we call as the homogeneous transform, T of 2 with respect to 1, right? The second camera with respect to the first camera. Now, once we have that, we also reconstruct based on the matches between the two views, because we now have the pose of the second camera with respect to the first. So we do a reconstruction. And this reconstruction will be up to scale. It will not be in the actual scale in which the camera moves. It's not going to be in the actual 3D scale, right? It'll be in some scaled version of it to maintain that scale. So we don't go through this pipeline once again, but when the third image is brought into play, so we do this extrinsics or camera resection, which is making use of the 3D points here and the 2D points which are tracked from the second image onto the third image. We solve for the pose of the third camera, basically in the same frame as the first camera. Like the first camera is often considered like KI0 or the identity. So this process keeps repeating, and then you have a bunch of what we call as the relative pose T1, 2, you get T1, 3, and therefore you get T2, 3, and Tn, n minus 1. And then you do a final optimization, which is famously called as the bundle adjustment. And then we output the optimized trajectory and optimized point cloud. So this is the staple SLAM pipeline. And then, of course, it can be modified with point clouds. It can be modified with stereo SLAM and all that. Right. So I will go through some of these, starting from projective geometry itself, because we are dealing with a monocular camera, but I will be going a bit fast. And so wherever, if you're not able to follow, we can take it up at the end of the class. Right. So now this is the standard camera, thin lens projection. Right. There is a point Q on the tip of this flame of this candle, and then that's projecting onto the image as this image pixel Q. And then you write this Q as a vector from the camera origin as some QX, QY1, and then you relate this 3D point to this 2D image pixel through this camera intrinsics K matrix, right? So and if you bring in the extrinsics into play, you will say the 3D point X as XYZ1 is projected onto the image pixel UV1 or small x, small y1 through this P matrix, which is the extrinsics matrix, which contains this intrinsics as well as the extrinsics. Now, this is, of course, given in a very nutshell. So I'll go through my notes. So when I switch, I'm also going to switch between, several things. So please bear with me. And when I come back, I think I have to go to the full screen mode. It's not very clear. And, so this is not coming now. So I have to keep doing this. So if you're not clear how that equation itself comes, I'll quickly run through this. So there is a point P, X, Y, X, W, Y, W, Z, W, and of course we add on 1 to it. And then that's projected onto this image, and there is this camera which with the coordinate frame X, Y, Z, following the right-handed convention. And of course, the image frame is only X and Y. So basically, this X and Y will be parallel to the XY of the camera. So from simple, like similar triangles, so basically you project this onto this plane, and you will get one set of relation. And you project this point onto the XZ plane, and you'll get another set of projective equations. And from those equations, you can actually get something like this, which is ZX, ZY, Z, where XY is the image pixel, right? As F, the intrinsics times the point, XYZ. And then you can actually take the Z out, which is to say we get the depth out, and then we say lambda XY1 is KX, or we say lambda times the X vector. So this, of course, is after you get it into this homogeneous representation, right, times KX. Or we call this as the central projection, which is X is, because lambda times X is in the same direction as X, is X is parallel to KX, right? So this is, and at this point of time, X is in homogeneous coordinates, or it is what I call as the analog coordinates also, in the sense the image point is in the, if the world point is in meters, the image point would also be in meters. If the world point is in millimeters, the image point will be in millimeters. So to get it to the digital camera image pixel coordinates, so there is this scaling which happens through alpha, which is basically this alpha is bringing the sensor width and things into play. So once you do that, so you will get a relation of this form, Z times UV1, where UV is the location in the image pixel coordinates relating to the X, which is in the 3D world coordinate through this equation. And then so we say lambda UV1 is K times X. And sometimes we get the lambda on this side and write it through the inverse depth formulation. So you can also say UV1 is some lambda times Kx, where if it is on the right side, then that's the inverse depth. This, of course, assumes that the image coordinates are in the center of the image. So the origin is, we are 0, 0 falls on the center of the image plane. But if you say the center or the image coordinate frame is on the top left, and then if the center is U0, V0, then you will get a relation such as this. And critical point here is any gamma X will also project to the same point, which is to say, if you scale on that 3D array, so gamma X will also be lambda gamma U gamma V gamma, so you can take lambda gamma out. So which is to say we lose this depth information through this projection, right? So basically, so this is one equation which we will come back to in terms of the reprojection error. So which is to say that X is parallel to Kx, and lambda X is equal to Kx. And this also is often used in image warping. So you can take the K inverse, and then you can say lambda times K inverse X is same as the 3D point X, the position vector X. And you can also say often K inverse X is parallel to or points to the direction of the 3D vector X. So these are standard, it goes into all the modern photogrammetric deep learning frameworks for aligning depth. And if you go from SFM learner to DPO and DPO, pixel SFM, all of them make use of this business and projecting back into the second camera, right? So this is right. So you can also bring in the extrinsics. So now if you are seeing a world point here, so let's say there is a world point XW in the 3D frame, and this camera is represented with respect to this world point through this homogeneous transform T of the world with respect to the camera, right? And so then you can write lambda XC as, because this projection, when you write the projective equation, this K will operate on a vector which is in the camera frame. So anything in the world frame is got into the camera frame through this homogeneous transform. And now you have this K times TWC, or we write it as in this particular case, XW is 4 cross 1, but you can also write it as KRT XW 3 cross 1, where we drop that last 1 from the homogeneous representation. So this is a 3 cross 4 matrix, right? And which is what is mentioned here, right? So, okay. So just to give an idea of what this SLAM thing is, I'm not going into the full scene mode because, so this is what we want to do, which is to say, right, so there is a camera which moves. I'll play it from the first. So there is this 3D cube, and the camera moves around this 3D cube, right? So this is the cube as seen in the second coordinate frame. So this is after we do the extrinsics. So there is a point XW. So this cube is in the world frame, these pixels of the cube. And this point cloud is in the second camera frame after you have done the extrinsic operation. And then when you operate this K on this points, which is on the second camera frame, you will get the image of the cube, of course, stripped of all the intensities in the second camera, right? So this is what happens when you move a camera around, what you call as the pinhole camera, right? This, of course, is the pinhole camera model. So it, let me, don't have the control. So it goes around, and like this is the projection on the 10th image, and this is the cube as seen in the 10th image, and things like that, right? So the agenda is in SLAM is from these images which you saw to recover this full 3D point cloud back, right? So this is what we want to do in any SLAM pipeline, is also to estimate the camera motion and to be able to recover this set of 3D points, right? So again, go back to this full view and okay. So back to this extrinsics, those KPX is what I quickly went through my own class notes to show how it is derived. So if you are keen on that, I can share that with you. So that says how a projection happens from the 3D to the camera view now, but now the camera begins to move. So you also want to relate the second camera with respect to the first camera through the epipolar geometry. So the epipolar geometry is the geometry that relates the camera and the points in 3D and the corresponding observations in the image. So basically here what we try to say is a ray that is going through the first camera to this 3D point P, when imaged by the second camera, will be imaged as a line because lines project to lines in pinhole camera. So this line we call as the image of this original ray going from the camera center to the 3D world point. And we also call this as the epipolar line, where the epipole is nothing but the image of the first camera as seen in the second camera's image. And then, of course, you can do the same operation on the first camera, which is to say you are imaging the line going, the ray, which is viewing this 3D point from the second camera, right? And you get another epipolar line and the epipole E1, which is the image of the second camera origin seen in the first camera's image. So the epipolar geometry is, the umbrella or is the container for all concepts like fundamental matrix, essential matrix, and chirality and things like that. So the epipolar plane is the plane P01, O2 is the epipolar plane, and then there is generally this relation which is P transpose FP dash, or you can call here with respect to this P2 transpose FP1 or P1 transpose FP2 equal to 0, right? And we will see how this relation comes. So basically what it says is for any point P in image 1, So this point P lies on the epipolar line corresponding to this in image 2, and that line itself is given as F transpose P. So the same thing here. So if you have a point P, which is viewed in the first camera, and this point P projects, so this point P is constrained to lie on this line, which is the image of this 3D line seen in camera O dash. And then basically you search for this point in this line, which is what happens in stereo as well, where the epipolar lines are horizontal and they are row-wise corresponding between the left and right cameras. And then you do some matching algorithm and find out where the correlation matches the best, and then you get this point correspondences. Now, having gotten the point correspondences, there is a relation in terms of geometry between these two views, so which is what we will deal with, right? So as I said before, many of these slides are taken from Cyril Stackner's, Feifeli, and maybe even Scaramouche or somewhere, and our own notes which we have made, right? So let's say this is the first camera, and by now, like Ki0 is the extrinsic, this is the extrinsic matrix, and this is the intrinsic. So this is your P matrix. So M is Ki0, which is the first camera, projection matrix P. I can write this P in terms of normalized coordinates by removing K. So which is to say, once the image is formed, I multiply the image pixels by K inverse, which is to say that I am removing all the camera action on it. Then the points are supposed to be in the normalized coordinate or normalized image pixels. So now the reason why we do this is also similarly, the second projection matrix is called KRT, and I can actually remove this K, which is to say I can multiply the image by K inverse. So I get a set of normalized pixel locations, right? And in such a case, so I can do this now in the 3D world itself. So which is to say that the so this point P dash, because now it is in the normalized coordinate, normalized pixel coordinates. So P dash is the ray which is passing from O dash to P. And if I know the R and T of the second camera with respect to the first camera, so RP dash is this ray as seen in the first camera origin. And then RP dash cross T, the T is of course the second camera with respect to the first camera. RP dash cross T will be a vector which is normal to this epipolar plane O dash P. And now because OP dash is, which is P transpose, lies on this epipolar plane. So basically its dot product with the normal to this plane is going to be 0, right? So this is the fundamental or the essential matrix relation. So we write it as P transpose T cross RP dash equal to 0. Sorry, this T is the translation vector, right? Not the homogeneous transform matrix T, right? So now any cross product can be written as the skew symmetric matrix times the vector. So we call it as P, the skew symmetric matrix corresponding to T times RP dash equal to 0. And then therefore we say this T cross R is the essential matrix that relates the normalized pixel coordinates from one image to the other. Now you can get back this, you can now get it back to the original coordinates because P was K inverse P. Now you can actually multiply by the original K inverse to get it back into this into the original pixel locations, and that relation is K inverse transpose T cross R. You can forget this K dash because that is if the second camera intrinsics is different from the first. So this relation is called the relation which relates the fundamental matrix between the two views. So the fundamental matrix directly operates on the image coordinates, the pixel coordinates. The essential matrix operates on the normalized pixel coordinates. So that's the only difference. So the K is stripped off in the essential matrix. So this is the relation, and actually, I mean, I do not know if anyone knows, this is of course Abhijit Kundu, who started computer vision in RRC along with Ankur Handa. So if you go and type Ankur Handa, Abhijit Kundu, you will see that they are extremely famous. Ankur Handa, of course, is, came up with this initial Lie algebraic layers for in computer vision, through the what do you say, GVN and toolkit for deep networks which can make use of Lie algebra. So he did his PhD with Andrew Davison and then joined OpenAI. And Abhijit Kundu, of course, is in Google research. He did his PhD with Frank Dellart in Georgia Tech, but let's say he kind of got introduced to computer vision through himself, maybe when he worked in our lab from 2008 to 11. Right, so the idea, of course, is not to talk so much about Abhijit Kundu, but then, right, so this, of course, it's good to talk about him, but let's say, so there is this, I'll come back to this later, these are corresponding pixels, and I think I'm not able to, and so this is the flow vector, and so these gray lines are the epipolar line corresponding to these pixels, right? So I'm, for example, if you think of a coordinate pixel here, so there is, I think, an epipolar line that corresponds to it. And where there is a sharp, these blue lines, they are the points which are not obeying the epipolar constraint because those points are in motion. So and where these red points are lying on the gray lines, those are the points which are obeying the epipolar constraint. So these are the stationary points. And this is, of course, what Abhijit did very immediately as soon as we joined the lab to segment moving objects. So we'll just show that later, where you can use fundamental matrix or multi-view geometry to achieve pretty good motion segmentation on a robot. So this, we just said how, what is the relation P transpose FP or X transpose FX equal to 0, but we didn't say how to compute F. But what we can do is from a pair of corresponding points here. So these correspondences can be achieved through, in this particular case, through a KLT tracker between two image pixels. So a pixel here corresponds to a pixel here, and through the KLT tracker or the optical flow track. And these are done, much prior to the deep learning era in 2008, 2009 to be more precise. So for any pair of correspondences between x, y, 1 in the first image and x dash y dash 1 written in homogeneous representation in the second image, where the correspondences, as I said, can come through optical flow or KLT tracker or SIFT correspondences, then you can write this X transpose Fx equal to 0 through a dot product relation like this. And then if you have, say, 8 such correspondences, you can write a matrix AF equal to 0. And so this relation, of course, is a homogeneous relation. Therefore, A will be rank efficient. So because any lambda AF will also satisfy this equation. So which means that F can be only determined up to scale, right? So F loses 1 degree of freedom. Actually, it loses another degree of freedom also due to the what do you say, the SVD, the singular value condition, right? So now, if you have pixel correspondences between two images, so they are this matrix is not well conditioned because some of them are in the orders of 10 power 4. Some are when you multiply 2 pixels, you will get a value like 10,000. When you have only 1 pixel, you have like value of 100, sometimes 1,000, and then the last row is 1. So to handle this, there is a kind of what we do is we transform this image, 0, 500, 700 to image which goes from -1, 1 to 1 minus 1, and then on that image we compute this fundamental matrix F, and then we also tackle this so-called null space constraint because the fundamental matrix is rank deficient, and therefore we do an SVD on this fundamental matrix and then find out the original estimated F, and find out the closest fundamental matrix to this original estimated F, which is, as a matter of fact, you do this, you retain this U and you retain this V of the original estimated F and replace, just remove this sigma 3 with 0. And this is the closest fundamental matrix, or the matrix which lies on the manifold closest to your estimated F. So, I mean, like the details of this derivation, you can see in Invitation to 3D Vision or Multi-View Geometry by Hartley and Zisserman and things like that. So I'm not getting too much into this. Once you know F, you can also estimate E through the method which we already saw. And then this E can be decomposed into 4 possible R and T. And then the best possible R and T can be found out by where the, by looking at the camera ray, if it is going forward and if the depth is possible. So there are standard, all this OpenCV, Open3D have very good source codes which do these for you. So if you look at the code, you would understand what the chirality constraint is. So now where we are, so we have 2 views, right? So which is to say I've quickly shown, I hope you will agree that we have found out how to find the second camera with respect to the first camera and all that. And now, once I've found the second camera with respect to the first camera, and I have the correspondences through the KLT tracker, then I can triangulate these correspondences to give me 3D as an initialization for the 3D. So the triangulation formulation is how to compute the position of a point in 3D space, given its image in 2 views. And we do have the camera matrices if you KI0 and KRT. And now we would like to estimate this 3D. So the basic idea is if you recollect this K inverse X is the array which is parallel to the 3D point, and lambda times, if you multiply K inverse X with lambda, the depth, you will actually get back to this 3D point, right? So from the first camera, I think I'll just go through this. Right, so these are 2 points, x1 p dash x k I0x, x2 x2 y2 z2 is p2x k r12 t12, which is the first the point as seen in the second camera. Oh, sorry. Okay. Okay, let's see. Let's take. So let's say this x1 is a projection of this point here, x, which is in the first camera, and the same point projects to x2 in the second camera, and you are observing this point from the camera origin P1, P2, right? P1 is k times I0, P2 is k times R of 1 with respect to 2, and T of 1 with respect to 2. And now this vector F, which is along this ray, is lambda times k inverse x1, ray through x1 meeting at point F. So this, so this is, and G is mu times k inverse x2. This is meets at G, right? So F and G, small f and small g, are the position vectors of the points F and G, which should in principle refer to the same 3D point X, but do not due to errors in K, R, T. So we need to get this F and G in the same reference frame. Only then they refer to the same point X. So basically, we do this transformation of G into the reference frame of F. So you have R is K inverse X1 and S is R12 K inverse X2, right? So basically, so we get 2 rays, R and S, and we want to see the shortest distance between these 2 rays, R and S, right? So basically, which is, we can say G minus F times R equal to 0 and G minus F times S equal to 0, and then we solve for this to get the location of points F and G. And if you drop the perpendicular between F and G and take the midpoint of it. So that will be the triangulated point. Okay. So this is in short triangulation. So as to speak, if you know, like, of course, I went through it a bit fast, but I can, if you are interested, I mean, in these notes or something, I can share some of them with you, right? So basically what we are trying to say is we have Ki0, we have estimated KRT through the method of fundamental matrix and essential matrix. So we back project the ray into 3D, and these rays are expected to triangulate to that same point X, but they would not. So we kind of estimate F and G, right? Through we solve for this position vector F and G, which is essentially we are solving for lambda and mu through a couple of equations which you get here, which is G minus F times R equal to 0 and G minus F times S equal to 0. We solve for this to get lambda and mu. So once you get lambda and mu, you get the depth, and you will get the point back in 3D, but those two 3D points will not meet. And then you take the perpendicular between those two 3D points and take the midpoint of that as the actual 3D reconstructed point. Right? So this is the notion of triangulation. So just to you know, keep you you know, like to keep you engaged. So we have done the first 3 parts of this pipeline, which is to say, if you want to quickly, I mean, I think, okay, let me not get into that. So, so we have done epipolar geometry, we have done triangulation, and if you remember this pipeline image, let me, I think I rather go to this. So we have done this as a matter of fact, and we have done reconstruction as well, at least one kind of reconstruction. And then we would look at resection right now, which is in the third image, given the points reconstructed from the first and second image, how do you actually estimate the third camera with respect to these reconstructed points? So all of this, of course, there are codes available. If you want to do resection, you can look at P3P, PNP or EPNP solvers are there. They are Grubner basis solvers, global optimal solvers, and you can also do it as a minimization of reprojection error in Ceres as the backend optimizer, right? So so the resection now is to recover the camera given 3D points and the corresponding 2D points in the image. So P3P stands for the projective 3-point algorithm. Given 3D and 2D correspondences, we need to find the extrinsic parameters of the camera in the frame in which the 3D points are represented. So if the 3D points are represented with respect to the first camera or the starting frame, then we recover any nth camera in the same frame as the starting frame, provided we know the correspondences between the 3D points and the corresponding locations in the 2D image. Of course, in the 2D, the tracking is happening via KLT or SIFT or OR, and then so we are tracking the points in 2D, and of course the points, and we know where these points are in 3D because we are also reconstructing them, right? So this I will for you know, because the way this is done, there are the best way to solve for this is through Grubner basis, which I also do not understand, which is a global optimal solver, which represents the rotation matrix as a polynomial and then solves for it. But this is a very simple trigonometric way of looking at the problem. So you have x0, which is the camera location, and you have 3 points x1, x2, x3, and you know the distances between those 3 points. And you also know where these points are projecting in the image as x1, x2, and x3. Now you want to find out the magnitude of this x1, x2, x3 such that it meets this x1, x2, x3, and also solve for the angle between these vectors alpha, gamma, alpha, beta. And that kind of is the problem of resection. So you can write this r times xi minus x0 is the point seen in the, xi minus x0 is the point in the world frame of the 3D point, the position vector from the camera origin to the 3D point xi in the world frame. R, of course, gets it into the camera frame. And now xis is k inverse xi, okay, which is a vector in the direction of this 3D point xi seen in the camera frame. And we do a different kind of normalization here because we want to recover the magnitude but not the depth. So we normalize k inverse xi into a unit vector k xis, and then we want to solve for this magnitude of this unit vector, right? And and the way we do it is, so we want to solve for this S1, S2, S3, and we have this cosine relations. Like you can write cos gamma, the angle between x1, x2, x2, x3, and x3, x1. So we get three relations, and you will actually end up getting equations, polynomial equations like this, because cos this, and and then you solve for these equations. It leads to 4 possible solutions, and then you can solve for there is an ambiguity which can be resolved by making use of a 4th point or something of that kind, right? So this is the in nutshell resection. Of course, I'm going through this quite fast, but there are I can always send you the slides or material corresponding to it. Now, finally, what we have here is a set of 3D points and a set of image, the camera trajectory coming from epipolar geometry. And the final thing is bundle adjustment itself. So bundle adjustment is a state estimation technique, right? So basically what we have is this point X, which has been seen over several cameras. We are showing only P1, P2, P3. We have estimated P1, P2, P3 through the method of essential matrix and resection, which is to say, we track these points over the image. We have P1, P2. We triangulated this point. We got this point, so we got all these points. And these points are tracked in the image. And given the set of 3D points and these set of image points, we do resection to get P3 in the same scale in which P2 is shown with respect to P1 and the same scale of the 3D points. So once now, I imagine you have several such cameras, and now we want to solve globally for these cameras as well as the 3D points themselves through this equation, right? So as we solve it as a nonlinear least square equation by minimizing this reprojection error. So when we do this, so we have, this is the very famous reprojection error term, Pi times xj multiplied by the inverse step will predict where this point will project in that particular camera. And we also have the observation of the camera on the image. So this projection of the 3D point should be close to this image observation. And this is the minimization of reprojection error. So for a single point, this will have 2 terms, one corresponding to the x pixel of the x coordinate of this pixel xij and y coordinate of this pixel xij, right? Xij is xij yij, which is the jth point seen in ith camera, right? So the projection of the jth point in ith camera is xij, and that has 2 locations, xij, yij, and then you will have 2 such residual terms corresponding to that. So which is what we write it as x11 minus x11. So this is the residual of the first point seen in first camera, the x coordinate of that pixel. So this is the residual f11, and then Similarly, for y11, you have another residual. Right? Similarly, there are residuals for all the endpoints as seen in the first camera. So you get 2 times n residuals. And then because there are m cameras, right? So this is moving over m projection matrices. So you will get 2mn residual vector terms. Then we know once we have residuals, how do you do it? So you do standard nonlinear least squares, do Levenberg-Marquardt or Gauss-Newton, and solve for this. And of course, the thing here is how to compute the Jacobian itself. So the Jacobian is obtained. I will do the very straightforward thing, which is we are not taking the Jacobian over the manifold, over the Lie algebra. I would also show how that is done. But we do the Jacobian over the camera projection matrices, right? So we have for Fij, which is the jth pixel, jth 3D point projected onto the ith camera, and the x coordinate corresponding to that. So Fij is that relation. F11 is the reprojection error term corresponding to that, or Fij is for that. Then I take the Jacobian of that with respect to the Pi, which is the ith camera matrix, and Pi is a 3x4 matrix, so you will get Jacobian like this. And Gij is once again the jth pixel in the ith camera, the residual corresponding to the white location of the pixel, and then you will get a Jacobian like this. And then you also get the Jacobian with respect to the 3D locations itself, because we are optimizing both for the 3D structure and the camera, right? So then this Jacobian can be written like this, so which is the motion Jacobian and the structure Jacobian. And we essentially solve for basically, right? So 3n times 6m, right? So this is the number of points we are solving for. Right? Basically 12m plus 3n is the number of points, but this is over parameterized. So if you solve for this, 12m plus 3n is the number of, so we get all the m projection matrices and n 3D points, but these projection matrices are not giving you the R and T. One simple trick is to just multiply that with K inverse, because we know the K, and then the structure there will be close to R and T, but not precisely so. To do this, we need to do this optimization over the Lie group, and I will just say in point cloud SLAM how it is done. The point cloud SLAM is the same thing, but now we start directly with point clouds, and there is a feature correspondence which you can get through ICP, which I think Professor Avinash might have covered. So once again here, so you have n point cloud, so you have these n correspondences, and you have the n transformations between one point cloud to another. So these set of trajectories can go into a backend nonlinear optimization, and you can get this optimized point cloud and this optimized trajectory, right? So this, of course, the ICP, I'm not getting into it, which is now we are not talking about a monocular camera and trying to do all the reconstruction, resection, all this is taken away. So this game is more easy to play, and we are directly having point clouds, right? I'm not going through this ICP, maybe because of shortage of time, but you can assume that given 2 point clouds, we can find how these 2 point clouds are related to one another, or how are the coordinate frames in which these 2 point clouds are represented aligned with one another. So that's ICP for you, and that will give you T1 with respect to 0, T2 with respect to 1, and this. And essentially it can give this whole trajectory as you are getting a point cloud of this tree and a particular point on this tree, right? So if a set of endpoints are viewed in M frames, what is the best estimate for these endpoints and these M frames, which is once again the problem of SLAM posed indirectly in 3D world. So instead of reprojection error here, we get directly this kind of relation, which is Xij, which is the jth point represented in the world frame as seen in the ith point cloud, which is the jth point. So it's like, let's say I'm moving towards a tree and I'm getting 3D point clouds of this tree, and I get a point cloud of the tree seen in the ith frame of my motion, right? And then I am estimating this Tij through ICP, And I can now predict where I would see, because I have this ICP giving so I can predict where I would see the jth point seen in the first point cloud or the 0th point cloud through this transformation in the ith point cloud. And then actually in the ith point cloud, I'm seeing that as well, right? Because let's say you are able to track these point clouds through ICP or PointNet or PointNet LK or one of these, there are a lot of deep networks which say how you can track point clouds. Now, if you do that, then you will have this kind of cost function that you want to minimize. And this is once again a residual running over n points and over m point clouds. Now, the number of optimization parameters, once again, if you're having m point clouds and n points is 12m plus 3n, because this transformation matrix is, is a 3x4 matrix, literally, because the last row is 0, 0, 0, 1. We don't consider the fourth row, but then this is over parameterized, right? So now we want actually to solve for it over the axis angle. So this is either you solve it over the axis angle or you solve it over quaternions. So now you write this Jacobian Jij as this residual with respect to the Ti and times Ti with respect to this axis angle. And once you write that, you will get this Jacobian in this form, similar to the bundle adjustment Jacobian, which is divided into the localization Jacobian and the mapping Jacobian. And the optimization is happening over the del vectors of the axis angle, right? So any rotation matrix can be converted into an axis angle through the Rodriguez formula or, through over the Lie groups. And then we optimize for del E1, del E2, and the 3D points itself, because we are optimizing for the motion as well as the structure. Now, this optimization, because you cannot take directly, you cannot add to, if you do nonlinear optimization, you have, or you do gradient descent, you say x nu is x fold minus eta times dou x by the dou of the cost function with respect to dou x and all. Right there, we are doing vector addition, and that vector addition is happening over an Euclidean manifold, so as to speak. But when you take the derivative with respect to a rotation matrix, then this has to, you can't add rotation matrices. So I cannot say the new rotation matrix is some old rotation matrix plus del of this rotation matrix. So that's not allowed. So what we do is we take this to the so-called tangent space, and I'm not getting into that here. One is because I'm not a math person, so we do, so we transform this to the tangent space, and we update the axis angle into the tangent space, in the tangent space, and bring it back to the manifold through a set of operations, which is called the exponential map and the log map. So basically, so this is the update, without getting into the details. So Ti0 n plus 1, which is the, like in the traditional nonlinear least squares, you will write Ti0 n plus 1 as Ti0 n plus del of Ti0. But when you do that, your Ti0 will not obey the properties of the transformation matrix. It will not be a rotation matrix and a translation vector. So we necessarily have to do this over the manifold, which is all hidden in the carpet. So, but the final update equation takes this form. Ti0 n plus 1 is Ti0 n times the exponential map of this axis angle, which is the most minimal representation of the rotation matrix. And then the axis angle itself is updated through the log map as log of Ti0. So a lot of things happen under the hood in bundle adjustment or structure from motion. But we don't need to know this if you use Ceres solver or you do post-graph optimization in GTSAM or GTO. So they will do this for us. We don't get into it. And now there are also a lot of layers in deep network which operate on Lie groups. So, so with this, I will stop the what do you say, the SLAM pipeline, which I have done for both monocular camera and 3D. Of course, it's the entire pipeline given normally we do this over 2 months in the mobile robotics course. So also in the summer school, we do it at leisure. There are assignments which help you figure out fundamental matrix, essential matrix, resection. And then we actually train people to use the Ceres solver for the backend optimization itself, right? Because that is very critical in robotics. So like we need to deal with these backend solvers. Like if a student is unable to do, then we can get stalled. But yeah, here of course it's a condensed thing, but I think the pipeline is. Well, I don't have an answer. I think both methods are there in literature, like operating over axis angles and operating over quaternions. I'm more familiar with the axis angle route, and the Ceres backend solvers. Yeah, the axis angle. Yeah, but you can use quaternions as well. I don't have an answer for that. Yeah. These are you just go through this exponential map and the log map. So I can send you, yeah, exp of this is the rotation matrix itself. So you can think of it as del R, right? So crudely speaking, exp of the del in the axis angle, when you do the exponential map, gives you a rotation matrix, which you can say as the new del R in rotation, which I can multiply with the previous rotation matrix to get the new rotation matrix. That is, of course, if you operate in SO3. This is in SE3, which contains both the axis angle and the what you say, the 6x1 vector, which is both the rotation and the translation. Yeah. So you can get it. Yeah. So there are yeah. So this Jacobian, I mean, I do not know if you. I mean, there is an analytical expression for this, but have we used it in the lab? No, we use the standard solvers for doing it. So Ceres is one solver in which you can. Yeah, so I think with this we will stop this point cloud, SLAM, and all that, and I will maybe go to the the research part of what we have been doing. So I'll start with a very old research, just because we brought this into play. And then go to new things which we have been doing recently. So, yeah, so this is moving object detection, which was what we did very early. I mean, this was, as a matter of fact, the first computer vision problem which we did in 2008, because when I started doing, I mean, when I started leading this robotics lab in 2005, I was not a vision person. I didn't know anything about cameras. I'd done only motion planning and things like that. But then, like the world imposes itself on you. So I started learning vision in IIIT. So 2008, luckily we had Abhijit. I mean, Ankur also had been there before. Ankur Handa and Abhijit Kundu followed in the footsteps of Ankur Handa, so as to speak. And 2008, he cracked this problem, as a matter of fact, in 3 months or 2 months. And it's pretty, it's not, I mean, like it is something like an evergreen video which we can show. And it's classical multi-view geometry, right? I mean, so basic idea is to detect moving objects from monocular moving camera. And this problem is actually tough if you look at it, because when the camera moves, the scene moves, right? So the static world moves and the actually moving pixels are also moving. Then you do not know which is actually moving and which is actually stationary. So the way to compensate for this motion is actually to compensate for the camera itself. So if I know how much the camera has moved, then I can solve for this problem. But because this is a monocular camera, this is not very easy to estimate camera motion, because like the process is difficult, and then the R&T you get are noisy. I mean, and then also like it's only done up to a scale. So what Abhijit did was he made use of this odometry on the robot, and the P3DX. The good thing about P3DX is has a very good odometry. So when this P3DX moves, he gets basically it's done in SE2. So he gets the yaw and the translation. And the essential matrix, if you remember, is T cross R, right? So he gets the essential matrix directly, right? And then he finds out which pixels satisfy the essential matrix constraint, which is P transpose EP equal to 0. And whatever pixels are not satisfying that constraint, he calls it as moving. Now, there is, of course, a problem here. It's not as simple, because there are a set of motions which we call as degenerate, which is to say, like, for example, this pixel, if this pixel were to move in the epipolar plane, so let's say this point P will project to X here and will project to a point P dash here. And this P dash will lie on this epipolar line. But if this P moves here, then this point, when it projects to X dash, does not lie on the epipolar line belonging to P. So this is the basic idea which he exploited. But however, there are a set of motions which lie on the epipolar plane itself, for which the epipolar constraint will be satisfied, but the point is moving. And that is called the degenerate motion. And so now he handled it with a flow vector bound constraint, which is to predict the flow I would have, because like this is the back projection and reprojection equation stripped of R and T. So I can predict what will be the flow for a particular depth, but I do not know depth. So he uses a Zmin and Zmax. So if the flow is outside of the bounds of Zmin and Zmax, he classifies that a pixel as moving. And then he develops a probability framework which merges this epipolar constraint and this flow vector bound constraint, and then implemented it on Pioneer P3DX. So this is really a robot from some other era, but the video itself has gone a little, what do you say, not so good. But so this is in 2008 December. But if you say, can you reproduce this result, is going to be very tricky. So there is a robot which moves, and there are other robots which are moving. And the KLT trackers on that object alone are segmented to be moving. And this is Abhijit himself. And you can see that scene is also moving, right? So this is, and it's a pretty good result. There is no deep learning. This is well before this era. And this is, you can do it with geometry, right? Geometry as exploiting the odometry of the robot to get the essential matrix. And you see the camera moves, the scene is moving, but we are able to extract only motion here. As a matter of fact, I think this was the first such video on a real robot which was done in 2008, and Abhijit kind of did it in 2-3 months. So whatever RRC is because of such kind of people who have come and played with me. I just hold forth at one end and others play around. I myself may not be really the person, right? But my students are somehow extremely, I mean, they're quite, I've been fortunate to work with really, really very good students over a long period of time. So, yes, so then, I will go to other things which we have been doing recently in what I call as the SLAM thing. So So I will start with this Satyajit's thing, which is recently, which we did this on a real warehouse scene. While we call it as opposite view loop detection and closure for, SLAM. Satyajit was also advised by Dr. Ravi Kiran for initial part of his thesis. So the SLAM comes in various formulations. So one thing which we did not do is the loop detection part. So basically, we have a trajectory like this, and then we have an estimation of the motion which can come from ICP or the robot odometry itself in this particular case, or GPS or monocular cameras, essential matrix, whatever that may be. So let's say I have a relation between these locations, right, or transformations. And now when I come here, if I ask where I would be with respect to this, I can, multiply, concatenate these transformation matrices, and I'll be able to say where I am with respect to this. But suppose I detect a loop, which is to say I see features in this particular pose, which are very similar to these poses, and I do an ICP between them, and then I get a new relation. So now I can optimize over this because the expected relation which I got from here was the new relation gives me an extra condition for optimization. And as a matter of fact, I can have several such relations, not just one, between various poses of the robot which moves around. And this is called as post-graph optimization. We don't optimize over 3D points, but we only optimize over the pose of the robot that moves, right? So this post-graph optimization, which brings in this loop closure constraints, what Abhijit did was he brought in this, the notion of topology into this. So what do we mean by this is, let's say, so if I have a topological understanding of a scene, like, let's say if you think of a warehouse, this topology is very repeatable. So you move between rack spaces, and then you move into corridors. And if I understand that I'm moving between a rack space and a corridor, I can either say that either I'm moving straight or I'm moving at a 90-degree or a 180-degree terms, right? So this notion of how you move can come from the topology, and which can be integrated with the standard post-graph optimization, because when you estimate this motion through ICP, you will not get this precise 90-degree turn or 180-degree turn, U-turn, or you're moving straight, because there is always going to be some error. But my understanding of the scene in which I move, which is coming through a deep network, can give rise to a new set of constraints, which we call as the Manhattan constraint, which we integrated into the post-graph to come up with an optimized post-graph. The typical post-graph, of course, is estimating the motion through ICP or any cartographer if you have LIDAR or any of the backend SLAM, right? So this is the basic idea. So we understand intersection, rack space, corridors, and then we do and then we know the topology in which we are. So we have a topology corresponding to each of these nodes in the post-graph, which is a location in which the robot is moving. At each location, the robot is viewing the scene, is understanding the topology. And then if this whole region corresponds to a rack space, then we represent it as one topological node with a starting and ending location. And then from a rack space, it moved to another rack space through an intersection. We represent it as an intersection node. And we know that these are related by a Manhattan world because you are moving in a Manhattan world. And therefore, there is a constraint which we call as the Manhattan constraint, which relates these two topologies. And this Manhattan constraint is optimized with the post-graph to get a new optimized post-graph. And this process is recursively done. And then we are able to recover from very deep odometry errors, right? So basically, there is a deep network architecture capable of learning warehouse topologies, a simple image classifying architecture. And then there is a multi-layer perceptron, which can compare two topologies based on only their geometry and say whether we are seeing the same instance of a topology or another thing. And once I detect a loop through this multi-layer perceptron, which compares topological instances, I get a loop closure relation, which goes back into the backend post-graph optimization. And then there is this two-way exchange between the Manhattan graph and post-graph to improve this thing. So this is how topological map. So this is a real warehouse thing which we got from a company with whom we were working. And you can see like the red is, so we have colored this, where the robot moved. So red color means the robot has moved in a rack space. The yellow means it's an intersection. Blue is like the corridor. And this is a topological classifier, which gives a label with standard ResNet 18 backbone, and the labels are rack space, corridor, or intersection. So it's fine-tuned over 356 epochs, and then training images or so many validation also. And of course, there is a class imbalance if you see that the intersections are much less than the corridor and the rack space. So he uses a class weighted loss, which weighs the intersection more. And then does a standard accuracy, I think, in terms of image classification accuracy on 2 warehouse data sets we had, which is pretty large. And this is the precision and recall for that. We also used an LSTM, which was not very helpful. So I'll just play this video. I hope it plays. I am connected to the, yeah. So this is just showing the image classification here as we move in this way. Right, so this is the odometry, which is, I think, coming here from a LiDAR-based cartographer, which is aligning, which is an ICP-based odometry, essentially, and the red points refer to the fact that the robot was in a rack space. So this is an area in a rack space. So for example, so we will be showing it as red. And when it comes to something like this, it will be an intersection or another rack space. So I think the intersection is shown in green. So the label is being shown rack space, a transition region or an intersection. It says this as transition. And then, transition once again, and rack space. Right? So this is the labeling which we are doing. And from this labeling, because we know where we are, we bring in this, let's say the original trajectory is unoptimized, the original post graph. So we combine these nodes and represent it by one topological node. And then we compute the angle between this through ICP. And because we know that we bring in this notion of topology, because we know I'm in this topology, I know like most likely I'm moving straight if I get some angle like 160 or so. I get a Manhattan graph for this, which is like this. And in this Manhattan graph, I do a loop detection comparison to say whether I'm in the same intersection, whether I'm in the same rack space, which I've seen before. I do an MLP-based instance classification. Of course, we could have used some other methods, but at that point of time, we just went with this. So this MLP is a Siamese network, which is only given the starting and ending locations of a rack space or a corridor or an typically, and then is trained over contrastive loss to say whether you are in the same topological instance or not. And once that is done, we put it together into the backend optimization and solve for the post or the trajectory, right? And so the final trajectory of the warehouse after this optimized post graph looks like this, and this is the LiDAR cartographer map for it, right? And then just to show how much the Manhattan graph can, so we deform the odometry quite bad, right? So this is how the deformed odometry trajectory looks, but with the Manhattan constraint and post graph optimization, we get an optimized trajectory which is pretty close to ground truth. So basically we say like even if your trajectory is so bad, which is like, your odometry is really awful here. But if I have an understanding of the topology coming through a simple image classifier and I use relations between them, then I can get an optimized post graph like this. So, and of course, we do a lot of ablations across various ways, and then of course, I'm directly presenting from Satyajit's thesis presentation, so we, I can possibly play a video here. So I think there is a video corresponding to this the SLAM optimization. Right, so, oops. Right, so this is the original unoptimized trajectory coming from an ICP which is corrupted. And these are the various loop relations we have between these trajectories or the Manhattan constraints which we have. And the Manhattan graph itself looks like this, but the Manhattan graph is not really the right graph because it's not really optimized. And but these relations are given to this post graph here, and we do a post graph optimization. And this is the true trajectory which the robot is actually undergoing. So despite we having a bad deformed trajectory here, so we can actually recover it through this understanding of the topology of the scene. Right? So this is the basic idea here, which is given. Okay. So I'll go to, because I think there is still around 10 minutes of time or a little bit more. So I will go through some other things which we have been doing, which is related to this, the SLAM pipeline, which is very related to this is Udit's thesis. So what we found out was when we come to a topology from an opposite view, like let's say I go out of this room and I come back into this room. And I would like to know that I have detected loop. So I go out of a corridor and I come back into the corridor from an opposite view. Right? Normally, any loop detection which works in SLAM, they have they believe that you are seeing the same view from a very similar looking scene, or the viewpoints are not very diverse, right? And there's also while SIFT is pretty much robust, but SIFT and also the classical descriptors can sometimes fail if the viewpoints are very opposite. Like I see this view and then I see the same scene from an opposite view. Can I get descriptor correspondences? And then if I get descriptor correspondences, then I can retrieve, I can say that maybe I'm in the same scene back in a very different viewpoint. And then if I can also solve for the post between the two views somehow through some post optimization framework or even standard ICP, then I can get this additional relation into my post graph optimization and improve this. So this is the basic idea. Sorry, I mean, it's still showing the old. So the basic idea here is to find out correspondences across very diverse views through a deep descriptor matching framework, and then integrate this framework into a backend SLAM system. So basically, there are two ways of looking at this deep descriptor matching for very different rotations. Like one is you can develop a rotation equivariant descriptor. So the basic idea is if I rotate an image by some amount, if I develop a rotation equivariant descriptors, those descriptors will also rotate by the same amount, which is not true in a standard CNN. Like if I have a CNN deep descriptor like superpoint or superglue or D2net or whatever that may be, or R2D2. So they may not actually, if the scene undergoes a rotation, the descriptor need not undergo the same rotation. So one way is you learn, you bring in this equivariant layers in your CNN modules and then try to develop descriptors which are rotation equivariant, which is a hot topic today. But another way of achieving this is also to augment the training data by giving a lot of augmented images, and we forcibly train this. So we are not training for rotation equivariance, but standard deep descriptors, we are actually training it to achieve the rotation understanding, so as to speak, right? So the second later thing is what we followed, and then we augmented the what you say the D2Net's training pipeline with rotation augmented images such as these, which is like, you know, like if you look at it, the front image, this is from the Oxford car data set. My mouse is not moving somehow. Right, so this image is from the front view. This is from the rear view. The cameras are very different. You see there is a lot of appearance variation. And the rear view does not look anything similar to the front view. Of course, we do an inverse perspective transform and get this road plane out. And then we get these correspondences, right? So most of the deep descriptors do not work well. As a matter of fact, SIFT can do a good job. There are, of course, descriptors like ORINET, which are affine transformations learned. It's a deep descriptor built, I think, over SIFT, or, you know, like they do give pretty good correspondences. But in this sequence, we found that in the Oxford car, you know, like even the classical descriptors like SIFT were not able to give these kind of correspondences. This is, of course, in our own scene, right? So when there is a lot of viewpoint change, typically the descriptors fail, and so we are handling this in this particular work, right? So we use 3 ways of evaluating it, which is one is the mean matching accuracy in the H patches data set, and then pose estimation on the diverse view data set, which is our own, and the use of rotation robust descriptors in VPR task. So we evaluated on 3 different data sets in 3 different modalities and show that our way of augmenting deep descriptors with this pipeline is really helping. So there is the standard D2Net pipeline, and then our own augmented pipeline, which we call as rotation robust descriptors, where we supply a lot of augmented data through homography, wherein we rotate, we do an in-plane rotation of the image by all kinds of angles. And then we know, because we know the homography for a pure rotation between 2 images is related by a homography. So we know the correspondences, and then we do this triplet loss and develop descriptors which are rotationally robust, which was not the case with Okay. Well, I am not myself, I know it only at the surface. Some of my students are working on it. So there is a lot of papers on scalable CNN, equivariant CNN, which are, and then there is also this. Yeah. So without doing any augmentation. This is D2Net. You can look at the D2Net paper, which is, I think goes through a backbone, and then at the end we have a vector, which is, and then Yeah, we have a descriptor vector, and we know the correspondences. The way D2Net trains is over the phototourism. They develop a SLAM backend. They use a call map and then reconstruct the scene. And then it's somewhat biased to SIFT and SURF, so like the correspondences are coming through SIFT. And then you have a, you know the correspondences. Now we learn the deep descriptors. The descriptors are so learned such that if they are the same in two views, they should be close to one another in some space. And if they are, you use the triplet laws or to get them closer and far apart. When they are matching, then they would be close. And that was through this, basically a warping formulation was done in D2Net. What we did to D2Net was we augmented a lot of homography rotated phototourism images where there is this descriptor correspondences are coming through homography. But in our case, because we constructed this homography, our descriptors are more accurate in terms of matching. Whereas when you do SFM on call map, the depth can also be erroneous, and then the back projection and then the correspondences, there could be more possibility of error in that way of doing it. But that's a more generic way, because if you do only in-plane rotation, you can only augment so much to this whole thing. But surprisingly, whatever we augmented on phototourism kind of worked on the diverse view data set without having to retrain with new augmentation. So basically, if there is a in-plane rotation, but for the Oxford car, we had to retrain again. So, but the basic idea is you have to go through an orthographic layer. So if the original layer is, original image is, like this, so we get an orthographic view of it, and on that, we learn this descriptor matching. No, I think this was augmented with fine tuning, if I'm not wrong. No, the only modification is this ensemble itself. So we have a kind of an ensemble architecture which is post. This geometric verification happens post, but the architecture itself is pretty much the same. Yeah. Yeah, so this is the one head is the D2Net and the other one is the RO-Hardy using self-supervised rotational homographies. And the basic idea is to get this orthographic view. How it is done is explained in this paper, and then we show it for these kind of road patches. So maybe I'll show a video. Let me see if, yeah, this ICRA, this of course is with its, I don't know if the audio will come. Let's see if I have to remove.
We aim to find precise pixel level correspondences between images under large viewpoint changes. Our pipeline takes in a pair of images taken from significantly different viewpoints. These images are then converted into orthographic images. The transformed images are passed to an ensemble architecture which comprises of two heads, vanilla D2Net and our system RORD. Visual place recognition is used to determine the robustness of our pipeline. Front image is used as a quick.
Yeah, so when I think use D2Net, so we get a lot of wrong retrievals. And of course, in this particular snapshot, ours is also wrong.
While rear images are used as references. We achieve the best recall compared to the other baseline methods. We evaluate our pipeline on the proposed diverse view dataset for rotation and translation error. RORD is able to showcase generalizability on this dataset in spite of being trained on the phototourism dataset. Results of extreme viewpoint registration.
So this work was funded by MathWorks. So yeah, acknowledging the funding agency. Now we want to it can be used in various ways, because once I'm able to determine really descriptors across views, one thing which we are looking at is to understanding the scene itself when I come from a very different viewpoint, that whether I'm in the same scene or not. And then if I know I'm in the same scene, then can I get a relation between the two scenes in terms of geometry, right? So where I am with respect to what I saw, like I saw a road from this view and I'm seeing a road from this view, and assume that there is no GPS. Can I still recover the pose between them? And then if I recover the pose between them, can I do better SLAM with it? So this is the thought process. I mean, of course, I may be thinking in a very robotic style, because that's what I've been doing, right? But then I believe this will have a lot of applications in augmented reality or VR. I do not know. Right? I don't know those areas. No, we don't have a network for orthographic view, which we use classical vision techniques. Yeah. So that is, the paper describes there are 2-3 ways we do. The standard way for a road scene is to do the so-called inverse perspective transform, which is quite common. So you take 4 points on the road and then say that they have to be a rectangle in the top view, and then estimate that. Something like that. So I think I'll stop here. So of course we have done many more things. I mean, or quite a few things in visual inertial navigation, multi-body SLAM in dynamic scenes and all. So SLAM is an area where we have managed to contribute for last several years, and that is kind of surprising because it's a very dense area. It's not an area where you can easily penetrate and continue to show something aligned with it, but which somehow we could do. So so I am very thankful to my students of really exemplary students who worked with me, and so that has given us some visibility in various. I thank them for what. Thanks. Thank you.
Thank you.
Thanks.
Yeah.
Thank you. Yeah.